Ngalakin kadijan yung nga boja.
We'll just start in a sec. I'm just waiting for my PowerPoint to fire up. Okay. Okay. So slideshow. Current. Okay. Okay, so can you hear me? So we looked at two-port elements. Now, so a lot of the course we're going to look at a two-port model for transmission lines, okay? And the main things to remember, okay, if we can actually make a two-port model of something, is that a particular port, okay, has two terminals, okay, and the main thing is we have to be able to assume that I in equals I out, okay. So that means that these terminals have to be what? Anyone? If we get the main consideration, the main axiom of circuit theory is that I in equals I out, okay? So what does that mean? That for a port consisting of terminals A and B have to be what? Anyone? What should they be? Yeah. The terminals A and B have to satisfy a certain property. Sorry? Yeah. So they have to be close together, right? Okay. So, you know, we can make, for this transmission line, even though it's a really long coiled up transmission line, okay, we can make a two-port model because A and B are close together. Also, C and D are close together, okay, so that's another port, so that will satisfy I in equals I out, okay. And actually, furthermore, all those ports are close together, okay, so it doesn't matter what you connect up here as long as everything's a very small distance away from each other, okay, and you can assume that, you know, the actual electrical signals propagate instantaneously throughout that circuit, everything will be fine, okay, you can apply circuit theory to that, okay. Now for this case, here it was coiled up in a small distance, but here it's a long distance, but it's actually spread out over a long distance as well. It's the same, okay? As long as the terminals are close to each other on a port, you can apply circuit theory, okay? In this case, we also got both ports close together, okay? So it doesn't matter what you connect up around here, you can apply circuit theory. And here's another example of transmission line. So can we apply circuit theory to this if we put it in a circuit? This particular transmission line here. So we have the ports on one side which are close together, okay, so that satisfies circuit theory. These ports also satisfy circuit theory because they're close together, but they're a big distance apart. Could we still use circuit theory to analyse a circuit with that particular element in it? Anyone? No one? Well, it depends, okay? We'll look at some examples later and see if that's true or not, okay? We'll look at some examples later about that, okay? Anyway, later we'll actually derive a two-port model for a transmission line, and S parameter in the Laplace domain it looks like this, okay? It gives you some idea. It looks nasty and complex, but we'll look at it later, okay? Okay. So we'll derive the transmission line model in the lectures, but you also look at measurements in the lab. Some of you have already done, okay? So look at these cases. A and B are local, C and D local and local to A and B as well in those cases. This case, we have A and B are local, okay, when close means close together. C and D are also local, but they're not local to A and B, okay, so it may put conditions on whether the circuit that we use that in can be analysed with circuit theory. Okay, so we're not going to cover linear circuits either this year. I'm just going to skip through some theorems that were in last year's course, but I won't cover them this year because you've had most of these in my course last year, okay, in the third year course. So you've had, I'm not sure we covered reciprocity, but we certainly covered Thevenin's, bisection and Miller's theorems, okay. So just quickly, reciprocity says that if you have some network, okay, and you have an input voltage to it, okay, and the output produces some current, okay, and if you put it in reverse, okay, you put the voltage on the output, okay, and you short circuit the input and measure the current, then you have this ratio between the currents, okay. So it'd look the same going one way as the other, effectively, okay. And note that the ratio of the transform of the responses to the transform of the excitation is invariant to the interchange of the position in the network of the excitation and response, okay. So, and if that's true, then it's called a reciprocal network, okay. And and that can apply to things like transmission systems for, you know, where you've got wireless transmission, you might have antenna and receiver, okay. So the actual network looks the same whether you're transmitting or receiving, okay. So that's just useful in some situations. I'm not sure we handled that last year, but it's just mentioning it now. It won't be in the exams, okay. Thevenin's, you covered that last year. I'm not going to go on about it again. I think we also, in the prac class this week, we'll look at that, okay, just to brush you up on that, okay. Norton's bisection theorem, you covered that last year. We won't be covering it in the course this year, but it's just in here as part of the revision. Miller's, because they're useful things to know. Miller's theorem, if you took the course last year, you'll definitely remember that one, okay, because it was in the exam. Okay, just talking now about physical electrical systems, okay. Thing of physical systems is that the real circuits have finite dimensions, okay. But circuit theory assumes no dimensions, okay. In fact, it's one of the axioms, okay. This I in equals I out means that for a circuit element, means that it has to have infinitely small size, okay. So it can't have any dimensions. So, you know, if we're going to use network theory to model things, we just have to check if we can actually fit our physical electrical circuit that we're going to make into this formal network theory framework, and if the axioms apply, okay. So we have to understand how to associate the abstract terminals of the elements in the mathematical framework with the physical aspects of the circuit elements, okay. That's an important thing, okay. And understand the nature of approximations that are involved. Okay. So here you might have some physical circuit, an element, okay, might be a capacitor, resistor, whatever, but it has wires, okay, connecting to it. And those wires have some finite size, okay, and they will have a finite resistance, okay, and they also have a delay involved with them, okay, because the speed at which signals propagate is limited by the speed of light, okay. And where there's a current flow, you have certain current densities, and actual resistance will depend on the frequency as well. Because we'll see later in EMT that you have things called the skin effect, where for higher frequencies, the actual cross-section of this wire looks less, okay. you may have potential differences in the actual wire, okay? So if you measure the potential difference at the terminals or at the ends of wires that connect to the terminals components, they'll actually look a bit different, okay? So it's important to understand sort of the limitations, okay, and the components you're using and the frequency you're interested in, and how well that approximates the real, the model is an approximation for the real device, okay? So, you know, typically, obviously, if you've got appropriate leads for the frequency and they're good conductors, you can assume that, you know, it's effectively a lossless wire with zero delay, okay? Again, this is the critical axiom, okay, that I in equals I out, okay? And it might be a good approximation when the distance between the terminals and element is not too large, okay, when the port is small, okay? We need to quantify how small is small, okay? So that's what we're going to look at here. So we're going to look at a signal, okay, and look at the difference between the signal and a delayed version of it, just to quantify how small is small, okay? So we can do that by looking at the first order Taylor series, okay? So if we have some signal h of t, okay, h of t minus tau, okay, which is a delayed version of h of t, okay, by delayed tau. If we do a first order Taylor series on h of t, we know that that's going to be equal to h of t minus tau times the rate of change, okay, of that signal, okay, at a particular time, okay. So you can see that how important the delay is depends on the nature of the signal itself, okay. So if we look at the magnitude of the difference between the signal and delayed version, it's going to be tau times the rate of change of the signal, okay? The delay times the rate of change of the signal. If we take a concrete example of, say a sinusoid, okay? So if there's amplitude A sine, it has amplitude A and frequency F, okay? Then we can say that, you know, we can normalize that difference. So we're interested in basically looking at the difference being a small fraction of the actual signal itself, okay? And have this epsilon, okay, which is just this divided by the amplitude. And we can do that, and we can see that it basically involves tau and F, okay? And basically the product of tau and F, okay? So we can go through and see that it is 2 pi f tau, right? And we want that say we want to make that smaller than some number, much smaller number. So we choose pi on 2, okay? And we can relate that to a distance and wavelength, okay? We know that the delay is simply the distance divided by the velocity that light travels at, okay, or the signals are travelling at, so it's going to be around about the speed of light. Okay, and so if we add all those together, okay, we want, so substitute tau into this, we get d2 pi f divided by the velocity, has to be much less than pi on 2, and we know that the velocity on frequency is the wavelength, okay? Okay, so we can express it in terms of wavelength now. So we come up with some condition that the actual distance between the terminals, or distance of a wire connecting the element to the terminal, has to be much less than lambda on 4, okay? Clear? That's a critical thing that we have to satisfy. Okay? So if that's true, then we can probably use, and where lambda is the highest frequency of significance in the signal, okay? May not be the actual clock rate or something, it may be, as we saw earlier, it's the rate of change of the signal that's important, okay? Not the base frequency, okay? So we saw earlier in the example of a clock that we had a very small rise and fall time, and that was effectively the highest frequency in the signal, and that causes, had the highest rate of change there. And that was the thing that we had to consider in evaluating what sort of frequencies the circuit had to work at. Okay, so it has to. So that has to be satisfied. Okay, so that we need these distances to be much smaller than a quarter of a wavelength. Okay. So this is about the dimensions of the port. Okay, but it doesn't say anything about if we've got a two-port model. Okay. Then we may have one port located in one position, another port located in another position. It may still be useful. You may still be able to apply circuit theory, okay? So it's just talking about the dimensions of the port, okay? We may have differences between the actual position of the ports. So if we put that in context, if you're talking about 25 kilohertz, okay, which is audio frequency, then you've got quite a bit of space to play with, 12 kilometres, okay, so you can have wires everywhere, and it's still going to satisfy circuit theory. Signals at one point in the circuit will be effectively instantaneously appear at other points in the circuit, okay. But if we look at, say, a printed circuit board, okay, then it's a different story. The boundless height might be a few centimetres or less, okay? And then the actual wire traces between the different components can't be considered to be small, okay? And you have to take into account the delay and also all the other effects that have come along with it that we'll talk about, okay? So also this one, remember we actually looked at this one. This has these long lines, okay, so they're large in comparison to the actual frequencies involved in the circuit, okay, the actual transmission line itself. But if you look at the ports, okay, they're small, okay. So each of those transmission lines consists of the wire on top of ground plane and a wire directly beneath that connects to the ground plane, okay? So the actual ports, the distance between the ground and the actual input, or the signal input to the actual transmission line is small, okay? So the actual ports on these transmission lines are small, okay? But the distance between the various ports are large, okay? So it turns out, of course that's true, we can still use circuit theory in this sort of system, okay? As long as we have a model for the transmission line which is spanning these large distances, okay? Okay, so we may have, putting in context a bit, just putting a graphical representation of what I've just said. So you may have large elements, okay, that span a large distance for the frequencies of interest, okay? But as long as the ports of those large elements are small, okay, and any interconnections are close together, okay, so we have small interconnect regions, okay, we can apply circuit theory, okay? Okay, so we can apply circuit theory in all these different areas, okay, because everything is close together, okay, where we have ports, okay? So in that region there, everything will propagate with zero time, effectively, okay, for the signals when thinking of the highest frequencies of the signals of interest. Okay, so circuit theory can be applied, okay, and here as well, okay. And we have two-port or multi-port models which describe, give a circuit theory description of how voltages and currents at this port are transferred to the other one. Okay, so we can apply circuit theory to all this. But remember that that also assumes that there's no actual other interactions between these large elements. Okay, that's the main thing as well. So that the second axiom, I think, said that the characteristics of an element depend only on the terminals. It's only characterized through the terminals or the ports. Okay, so you can't have extra interactions between here and here and here, which might occur if there was RF frequencies involved. And but we assume when we make the actual circuit theory model that the only interactions between elements are through the ports. Okay. Okay, so it's just another example of connecting, elements together and being able to do circuit theory. So we've got small terminal ports, they're close together. We've got small interconnection regions, okay, and we don't have coupling among elements beyond what is reflected in the multi-port model. Okay, so it means we can apply circuit theory. Okay, so we've got axiom 1 holding, axiom 2. We've got axiom 3 and 4, okay? So we can look at this system as an example, okay, to check the validity. So this might look like an op-amp model, right? Or an op-amp circuit. So in this case, if this 2-port was an op-amp, so you had the 2 differential inputs and you have an output that's with respect to ground, okay? And you have these 2 ports. They're close together. Actually, both ports are close together, and actually probably everything inside that's small compared to the wavelengths of interest. So would circuit theory apply to that system? Yes or no? Someone? Yeah, it would, right? Because everything's close together. Okay, they're all local. So we can apply network or circuit theory to analyze network. So say now we have a large coaxial cable wound up. Okay, it's long, and we've got the 2 ports A, B, and C, D. Okay, so could we apply circuit theory to that and solve? Anyone? Yes or no? Yeah, you can. Okay, because these 2 ports, this is local. This port's local. A and B, both terminals are local. Okay, this C and D is local. Okay, and A, B, and C, D is also local. Okay, so any connections between the 2 will also be small. Okay, would this also be? So it's only a small distance. Would this also work? Yeah, it would as well. Okay, it doesn't matter. Okay, A, B, and C, D are local. Okay, so everything in that circuit is in a small distance from each other. Okay, even though this transmission line may stretch out over a large distance. Okay, would this work? Could you apply? And this is stretched out over a large theory. Could we apply circuit theory to this circuit? No, you can't, right? Now the reason is that even though A and B is local and C and D are small, or close together and local, they're not close to each other, okay? So the issue comes here is that, where's the main issue here? What's the critical problem in this particular circuit? Anyone? Anyone? Okay, so it's the resistor and the capacitor connected across from this port to this port, okay? And we're assuming that for this resistor model, okay, we assume that I5 there is going to be the I5 coming out here, right? Okay. But it can't be because, you know, this A is a long distance from C, right? So we couldn't use circuit theory to analyse that particular circuit, okay? Because there's a large distance between the wires connecting that resistor. Okay? It's large compared to the wavelength of the signals of interest, okay? Okay. So we've got A and B are both local, okay, to themselves, but they're, and you know, we've got a 2-port model for it, but they're not close to each other, and we have sort of direct connections between the two. So that means something in here isn't going to have wires that are going to be small. Okay, it's going to have long wires connecting it. Okay, so the model for this resistor won't be correct. Okay, so can't apply network. Okay, so cables, multi-port networks, we'll leave that. Okay, so now we'll start on the next part, which is transmission lines. Okay, so that last one was a bit of revision and just to be clear about modelling and the use of circuit theory, okay, and how we can apply it, what are the limitations to be aware of. Okay, so we're going to do a few things in this particular slide set. We're basically going to try and derive a model for a transmission line using circuit theory itself. Okay, should get stuck into that in this lecture. Particularly, we're going to be looking at lossless transmission lines as the first part. Okay. Before that, I'll have a look at some examples of coaxial cable and PCB traces. Okay, and just give you an idea of the values involved. Even though you have to wait to we get to EMT to actually get the models for how we actually obtain those values. Okay, and then we'll look at analysing a lossless transmission line. Okay, and from that we'll be able to get a 2-port circuit model. Okay, and we'll be looking also at a frequency domain analysis of the transmission line. Okay, and we're looking at a special case, which is the match line. I don't know if some of you have done the lab, you would have seen that if you put a load, 50 ohms on that coaxial line, it becomes very simple. And if you put something else on the load, then everything becomes very complex and very difficult to interpret. Okay, so when you put the 50 ohm, it's called a match line, and that's something that we can analyse quite easily. Okay, and then we'll look at time domain analysis of lossless transmission lines. Just looking a bit, Tony likes to look at the thing in context in terms of history. So we'll just go through this. You don't have to know this for the exam. So the first telegraph line in Canada was actually made in 1846. I think it's probably the first main telegraph line ever. And the theory for, so you know, basically the practice occurred first, because people wanted to transmit information over long distances. And the theory for that was developed later by this guy, Lord Kelvin, okay, and he provides some mathematical basis, though he got it wrong, okay. His theory was incorrect. And in 1874, telephone was conceived by Alexander Bell, okay, and then they made the first long-distance calls from where he was living to somewhere in Canada, so it's Paris, Ontario, not Paris in Europe. And then it was 1881, okay. this guy. Have you heard of Oliver Heaviside before? Have you heard of Heaviside in anything? You know the Heaviside step functions? Yeah, that's where it comes from, this guy. He's really, really a good guy. And he was the guy that actually did the first correct mathematical theory for transmission lines, okay? And also proposed a way to actually improve the performance, okay? So he's a really good guy. And then later they actually applied that that way of improving the performance of transmission lines for actual transmission, okay? And that was so he was probably the guy that developed the theory for transmission lines and actually showed how they could be improved and used. Okay. So the goal is to determine the VI relationship of two ports of a transmission line based on analytical modelling, okay? So you've had, in the lab, if you've had it already, you tried to do that empirically, okay, by putting different stuff on it and looking at the waveforms, okay? If you had looking at transient signals, the observation time is important, okay? So you look at it for a long time, it looks totally different from what you see for a short time. And source impedance is important, load impedance is important, okay? If you look at steady state signal signals, the frequency will be important, okay? But so it's very difficult empirically to get a model, okay? You can't just measure it. It's not easy. So we need some theory to actually work out what's going on. So what we're going to do to try and use circuit theory to model a line is to just take a very small section of the line, okay? So we have a long line and we're just going to take a section delta x long, okay? It's going to be a uniform distributed line, okay? Or a uniform transmission line. Okay, so in the transverse direction, okay, so one is plus and one minus, so they're two lines together, or it's a line over a ground plane, okay? These are close together, okay? So obviously it's going to be small compared to the frequency of interest, okay? So the actual terminals of the port is going to be one here and one here. That's going to be small, so it's going to satisfy circuit theory, okay? And same on this side. And also, because we choose this to be small, we actually take it to the limit of 0. Everything in here will also satisfy circuit theory, okay? And we'll eventually see that we're going to have, for that little section, okay, we're going to have a model that looks something like this, okay? So, and you could perhaps see that intuitively because you've got two wires, okay? So you've got, obviously in a wire you're going to have capacitance between the two wires, you know, because they're two sort of flat wires close together. There's going to be some capacitance, so you can see where you can get some capacitance from, okay, between the two wires. A wire always has inductance, okay, so and it's going to be in series. So you have some inductance. You also have some resistance in the wire, okay, and you might have a dielectric between the two wires that has some current leakage, okay, so you may also have some conductance between the two, okay, so that's how you could imagine getting a model like that, okay. So each of those little sections there will be modelled by this part here, okay. So that's the one that comes before. This is the one here, and you have another one after this, okay. Okay. You also see in this slide we've made a change, okay. We could also consider those things to be at a certain frequency as well, okay. Okay, so it might, so and that's true in real life. A lot of these parameters are dependent on frequency, okay. But then it has a limitation, okay. When we put f in there, we mean we're just talking about the model that's applicable for one frequency, okay. But we'll look at that later, okay. Look at that later. So first of all, we're going to look at it frequency independent, okay, and then we'll look at it later in the frequency dependency, okay, just for sinusoidal signals, okay. But we'll first start off with frequency independent model, okay. So looking at actual transmission lines, so the one that you saw in the lab was a coaxial line, okay. So you had two conductors, okay, one with the outer one with hollow one with diameter RS, and you had some smaller one inside that was solid with radius RW, okay. And for EMT, we'll see later, okay, we do these equations, we actually get an expression for the capacitance per unit meter, okay, depending on the actual dielectric constant of the material between the conductors and the dimensions of the conductors, okay. And we can also, so that would be the C in our model, okay. And we can also, we'll see later in EMT, we'll go through this. We can also get the inductance, okay, which is this, which is phi on I, okay, so defines inductance, should write down L here, per unit length. It's also dependent on a constants times the ratio of the different radiuses, okay? We'll go through that in EMT, don't know that yet. And looking at PCB traces, which is what you're going to encounter when you actually make, if you're going to design printed circuit boards and design electronic equipment. You might have something that looks like this, okay? You typically have a reference plane, which is a ground plane, okay? And then you have these signal traces that go along perhaps the top or the bottom of the printed circuit board, okay? And more commonly nowadays you have not just two-sided boards, you have multi-layer boards, okay? And then they would have different layers to actually transport power or ground supply, the power or the ground, and you have the different signal layers separated on either side like this, okay? So the actual transmission line is formed with signal line and the ground line, okay? Okay, so that's the two ports, that's one here and one there, okay? And the actual signal propagates along those, okay? In the older days, certainly when I was a lot younger, that you'd have just printed circuit boards that just had wires everywhere but no ground plane, okay? I don't know if anyone can remember those or have seen anything like that. Could we model that as transmission lines? Yes or no? Anyone? No. Why not? It's not uniform, right? So the assumption was that when we had this model, remember we said a uniform transmission line, okay? So all down length it should look the same, okay? And here it's not, it would be changing everywhere, okay? Whereas on here, for a printed circuit board, go a bit further, effectively the signal wire interacts with the ground plane over some short area underneath it, okay? Because these distances are really small, so it's typically 1.6 millimeter thick here. This might be half millimeter wide, okay? And it's only interacting here. So all the signal wire sees is just this constant ground plane, okay? So the actual impedance and everything it sees, it looks uniform over the whole length of the line, okay? You don't see any changes, okay? Whereas here, it's not uniform, okay? So we can't develop a model for it would be very difficult, okay, for each line. So it's only those things, those sort of circuit boards are only good if the signals are very slow, okay? Have slow rise and fall times, and then the wires look like perfect wires, okay? They don't have to be considered as transmission lines, okay? So if we look at some typical characteristics, okay, we can see that this is for the microstrip line, which is a typical printed circuit board line that you'll use, okay? You can see that the characteristic impedance, we should talk more about that later, decreases quite a lot as you make the wire thicker or wider, okay? You can see the capacitance, as you make it wider, increases, okay? Capacitance per unit length. And that should be obvious as well, because as you make things, as the wire becomes wider, you make effectively the parallel plate capacitor between the ground plane and the signal wire bigger, okay? So obviously you're going to have more capacitance, okay? So I think you learnt last year, or we certainly will learn in EMT, how these physical properties relate to capacitance, okay? You can also consider that as you make it wider, you're putting lots of more traces in parallel with each other, okay? So we know that capacitors in parallel increase the capacitance, right? And as we make the width wider, okay, we make the inductance per unit length smaller, okay? So you could consider that intuitively by if you have lots of inductors in parallel, okay? They add up to make a smaller inductance, right? Okay, so perhaps we'll stop there. And next lecture we'll start on the actual telegrapher's equations, okay, for the lossless line. Okay, so is there any questions? Anyone before we leave? That's right. That's. I think that's a good point. So I think the Pratt classes are a good guide to the sort of things you're going to be asked in the exam. Okay, that's a good guide. You can see that. Especially these last slides, there's been more of an introduction, okay? So there's probably not a lot of examinable material in that, okay? From now on, it'll be more getting into the maths, okay? So there's going to be more things that can be obviously be put in the exam, okay? But you should certainly know, like, you might get asked questions. Does circuit theory apply to this circuit, or why not? Okay, so you should be able to recognise that. Yeah, I think I agree with you. So I'm using the slides from Tony from last year, and yeah, he spent even more time going through, looking at modelling and when you can apply it and things like this. But it isn't that obvious what's going to be in the exam from there. But I'd say most of that introduction, probably not. Okay, it's not going to be much. From now on, though, you'll start seeing a lot of stuff that can be put in the exam. Okay, that help?